Hello students and welcome. Today is Wednesday, January 6, 2021. Today's objectives are students to be able to write congruency statements for transformed figures, students to be able to determine if figures are congruent and, if so, identify their corresponding parts, and students to be able to determine unknown measures of congruent figures. Before we begin, please go ahead and complete today's Do Now. Today's Do Now is just a check-in, asking how was your weekend? Or your winter break, rather. For 5 bonus points, whether that be on an assignment or an exam, please go ahead and, if you choose, answer the following bonus question. What was one instance in which you used math over winter break? Please go ahead and complete the Do Now for approximately 4 minutes now. Today we're going to dive into Unit 5. This is our second to last unit in this course. Today's lesson is titled Congruency Figures. Let's do a brief review of rigid transformations. There are 3 rigid transformations: reflection, translation, and rotation. And they are known as rigid because they preserve the angle measures and segment lengths of figures. So the angle measures and segment length does not change between each type of transformation. So we know that these are rigid because they preserve angle measures and segment lengths. Congruent figures. 2 figures are congruent if and only if one can map onto the other by one or more rigid transformations. So either they map onto each other, meaning they are congruent to each other, the same, or if their angles and line segment lengths are exactly the same. So here we have a plethora of congruent figures. Let's look at our first set. Our first set tells us that ABCD maps to A prime, B prime, C prime, and D prime by a rigid transformation. We are told that a rigid transformation is taking place, so we in fact know that these 2 are congruent to each other. These 2 figures, the 2 green figures, are congruent to each other. On the other hand, in this one, we're told that QRST is congruent to Q prime, R prime, S prime, and T prime. Therefore, they are congruent to each other. We're being told that those 2 are, in fact, congruent to each other by this symbol right here. This means that QRST can be told to map to Q prime, R prime, S prime, and T prime. This can also be written like this. That tells us that QRST is mapped to Q prime, R prime, S prime, and T prime, and this is done by one or more rigid transformations. And again, we know that rigid transformations always preserve the angle measure and lengths. Let's move on. Now we have congruent figures and transformations. We're going to look at congruent figures and what it means to be congruent and non-congruent, and what different transformations can tell us about those congruencies. So let's look at congruent. Here it's told the triangle DEF has been rotated 180 degrees about point P, followed by a reflection across M. So we know we have a rotation and a reflection, both of which we know are rigid transformations. So because we know we have rigid transformations in both instances, 2 rigid transformations, it's easy for us to assume that DEF is congruent to D prime, E prime, and F prime, and D prime, E prime, and F prime is also congruent to D double prime, E double prime, and F double prime. So that also tells us that our original figure, DEF, would also be congruent to D double prime, E double prime, and F double prime. So through all of these different rigid transformations, our angle measures and our segments remain the same. So the congruency of all these figures is the same. Now let's look at when we have a non-congruency. Here we see that angle JKL has been rotated, so we have a rotation, 90 degrees about point R, followed by a deletion by a scale factor of 2. So here we see something new. And what we see that's new here is we have what is called a deletion. What is a deletion? Well, a deletion is basically an increasing or a decreasing in size by a specific scale factor. A deletion is not a rigid transformation. So here we do, in fact, my fault. Where was I? Okay. Here we do, in fact, have one rigid transformation followed by a non-rigid transformation. So we know that we only have 3 types of rigid transformation, which a deletion is not part of. Right? Our 3 types of rigid transformation are reflection, rotation, and translation, not deletion. So what does this tell us? Well, this tells us that we have congruency from our original JKL, which is congruent to J prime, K prime, and L prime. Not double prime, L prime. But we know that because we have a non-rigid transformation from J prime, K prime, L prime to J double prime, K double prime, and L double prime, that's because that's not a non-rigid transformation, we know that those are not congruent to each other. More specifically, as we can see here, the angles may be the same or may be congruent, like indicated in these lines right here, but our line segments are not congruent. If we increase the scale factor of this line segment by 2, a scale factor of 2, well then that means that our corresponding new line segments must be 2 times the original line segment. So as you can see here, we went from 1.5 to 3, where 1.5 times 2 equals 3. So that's increasing or deleting, doing a deletion by a scale factor of 2. Therefore, those two wouldn't be congruent because the line segment is congruent. Okay. So a deletion is not a rigid transformation because it does not preserve segment length, like we saw there. A single non-rigid transformation or a composition that contains a non-rigid transformation will not produce congruent figures. So anytime we have any type of non-rigid transformation, we can automatically assume that we will not produce congruent figures from our original figure. Okay, let's move on. So let's determine if figures are congruent. So here we are being asked, are D, E, F, G, and W, X, Y, Z congruent? Well, let's look at this a little deeper. 1 second. Okay, so here we are told that DAFG is translated 5 units up. So we have a translation 5 units up. And then D prime, E prime, F prime, and G prime is mapped to W, Y, Z, Y by a reflection across the y-axis. So what does this look like? Well, we'd have to look at the diagram we have. So here we are told that our original figure, our pre-image, here we have our pre-image, is translated 5 units up. So let's say we take D in this instance, we move it 1, 2, 3, 4, 5 units up, making our D prime. Again, we would take our E, move it 5 units up, making our E prime. G, same thing, F, same thing, thus giving us our image. So we know that in this instance, we went from DE, GF, which was translated to form D prime, E prime, G prime, and F prime. Okay, well then after that, we had a reflection. Well, we know a reflection is a rigid transformation, so we know that we have a congruent figure. But as we can see here, the name of those different vertices has changed. So we went from D prime to W. So D prime becomes W. We went from E prime to X. So E becomes X. We went from G prime to Z. So it becomes Z. And we went from F prime to Y. So that becomes Y. Therefore, we could write this as our original figure, our primes, were mapped to create our new image, which is just represented in a different way. More specifically, the vertices have just changed. But it is still congruent to each other because we did in fact perform a rigid transformation. So we have two rigid transformations, which means in the end we know that we're going to have a congruent figure, but we also know that we did change those vertices, so we can in fact say that these are congruent to each other. So what this also tells us is that we've kept congruency through all three of these. So this could also mean that we could say, if this is congruent to this and this is congruent to this, well then it's reasonable to assume that our pre-image would be congruent to our final resulting image because we did in fact have two rigid transformations. So that's what that tells us right there. We also know that now we have different vertices that correspond to original vertices. So what does this mean? Well, here we see that angle EFG, so let me erase it so we can identify it a little bit better. Angle EFG, so angle EFG would be approximately this angle right here, this angle. Well, we can see that that maps onto being congruent to this angle right here. So that just means that those two angles would also be congruent, just even though we changed those vertices, right? So we get EFG is congruent or corresponds to WCY. Okay, let's go ahead and move on. So now we're going to look at corresponding parts of congruent figures. This says if two figures are congruent, then their corresponding parts are congruent. What does this mean? For triangles, we refer to this concept as corresponding parts of congruent triangles are congruent. CPCTC. For polygons, we refer to this concept as corresponding parts of congruent figures are congruent. So CPCFC. Okay, so the only instances in which these terms change is we went from T to F. So if we have an F, we refer to polygons, and if we have a T, then we refer to triangles. Okay, but basically these different concepts allow us to understand the corresponding parts of those congruent figures. So let's look at this a little bit deeper. So corresponding parts of congruent figures. So let's see. Here we have a problem. We are told, given that ABC, triangle ABC, is congruent to DEF, list a pair of congruent sides and a pair of congruent angles. Explain why they are congruent. Well, here we have two congruent triangles. So we can go back and we have four triangles. We refer to their corresponding parts as the congruent triangles are corresponding parts. So CPCTC. So according to CPCTC, we can go ahead and because we know these triangles are congruent already, because that's what we're told right here, what we can go ahead and do is we can actually go ahead and find congruent sides and pairs. So let's look at those congruent sides and pairs. Well, it's obvious here that AB is congruent to DE. Oops. Okay. It's obvious here that BC is congruent to EF. It's also obvious that we would have our last one congruent to each other. So if we have two congruent sides, well then it's reasonable to assume that the third side is also congruent. We have AC, which is congruent to DF. Okay. And now let's go ahead and identify our congruent angles. Well, here we have angle B, which is congruent to angle E. So angle B is congruent to angle E. Well, if we know these two are congruent, well then we can also assume that angle A is congruent to angle D. And then our last one, C, is congruent to angle F. So that's basically all the different list of sides and pairs which are congruent to each other, or angles which are congruent to each other. And so basically what you're doing is once you know that those two are congruent, seeing what we highlighted here, we know it's congruent. Well, after that, what we can do is try to figure out how we can map those triangles onto each other and where those vertices would map up to create congruent sides and congruent angles, like you see here. Okay, well let's go ahead and take this a little bit further. Let us now determine unknown measures of congruent figures. Okay, so let's see what this says. This says, given PQRST is congruent to WXYZ, so we know we have two shapes which are exactly the same. The only difference is that those vertices are different. We now are asked to find the measure of all sides and angles of both figures. So we have, in this instance, figures, so we'll use CPCFC, right? We have two figures, not two triangles, so we need the one with the F. And according to that, we know that we will have corresponding parts and angles. So we want to identify what those different missing parts are, given that we know that they're congruent. So we know these two are congruent, so we want to see where they map onto each other. Well, the easiest way to go about this is here we're giving a little bit of a hint. Here we're told that we have a 90-degree angle at R. Okay, so let's look at our figure XWYZ, or WXYZ. Where there would we have a 90-degree angle? Well, it looks like a 90-degree angle would reasonably be located, right here. Okay, so what does that tell us? Well, that tells us that our R maps to where our Y is. So our R is basically congruent to our Y, or our angle R is congruent to our Y. Okay, well, let's take that a step further. Okay, if we know that both are 90 degrees, well then, let's go ahead and fill out the other missing parts. So what I would do is pick one figure. So I'm going to start with QRPS and map everything on QRPS to WXYZ. That's just the easiest way to do it. Okay, so we already have checked off that we have mapped that 90-degree angle. Okay, cool. Okay, now let's look at what's above that. We have 8 centimeters. Okay, so where would those 8 centimeters be located? Okay, well, we know that if those map, then we would have 2 congruent segments here. Okay, so that means that if this is 8 centimeters, then this would also be 8 centimeters, right? Because those are congruent. That's what those lines indicate. So our 8 centimeters would also map over here. So we also have 8 centimeters here and 8 centimeters here. And in doing that, we have mapped that whole side of that figure to the other figure. Okay, but are we missing something else? Yes, we're missing this 49 degrees. Okay, so where would those 49 degrees reasonably be located? Well, as you can see here, we already have 90 degrees here, 94 here, 124 here. So what are the angles left? Well, the only angle left is this one, angle W, and so this would map to 49 degrees. So therefore, we can check that off, and we have mapped it over here. Okay, so now that we have mapped everything on PQRS, what we can do is now go to WXYZ and map it back to the other one. So I'll choose a different color. And what is located on WXYZ that isn't already on PQRS? Well, as we can see here, what we don't have is 94 degrees. Okay, so where would that be located? Well, it's across from the 49 degrees, so it would be right here. And then we need the 127 degrees, so that's right here. Okay, and what else have we forgotten to map? Well, we've forgotten to map these two different lengths. So we need the 15. We know the 15 is above the 94 and the 49, which would be located right here. So we have 15. And then our last line segment that we need to fill out would be P and S, and that is 10.6, which we got from right here. So just by doing that, we've been able to transfer information from one figure to the next figure, showing their congruency, showing that they're exactly the same. The only difference is the orientation or the location of the different angles, right? And so it's reasonable to assume, or this helps us understand, that those two figures are in fact congruent. Okay, give me 1 second. Okay, so let's go ahead and move on to where we might use this in the real world. So here we are being asked to solve a real world problem, but in this case we have two congruent triangles. Well, if we have two congruent triangles, we know that we can use CP, CTC, which tells us that if we have two congruent triangles, well, then their parts of the triangle will be congruent as well. Okay? So, here we're told, Emma forms the frame of a roof for a shedding by combining two congruent right triangles as shown below. Find the perimeter and area of the entire frame. Okay, so what we want to do first is to fill in the missing parts. Okay, so how will we fill in those missing parts? Well, the easiest way to go about filling in those missing parts is to go ahead and map what we already given onto the other congruent. So we have a right triangle, so we know we have a right angle right there too. And because these two are congruent, we know that this line is also 3 feet on this side, and we also know that it's 4 feet on this side. Okay, wonderful. Okay, now that we know that, what we can go ahead and do is, if we need to find the perimeter in the area, what we can do is go ahead and find the area just by using the information we're given. So the area of a triangle, we haven't learned this yet, but we will go over it a little bit more, is represented by 1/2 the base times the height. So what does that look like? Well, that would look like identifying what our base of this entire triangle is. So our base is this entire length on the bottom. So 4 plus 4 is 8. So our base is 8. And then our height would be how tall the triangle is. So the middle measurement. And we can see that it is 3 feet. So we have 3. And so we would take 8 times 3 and then divide it by 1/2, or multiply it by 1/2. Either way works best for you. So basically, doing that, we would go A is equal to 1/2. This becomes 24. 1/2 of 24 is 12, so our area is equal to 12. Okay, so that's how we would solve for the area of that entire triangle. Okay, so now let's look for perimeter. Perimeter, like every other thing we've seen before, is basically adding all the sides together. But what we see here is that we're actually missing the sides of our upper regions. We don't know the length of this region and the length of this region. We know that they'll be congruent to each other because it's two congruent figures, but we don't know the length. Well, the way that we can solve that is by using the Pythagorean theorem. And basically the Pythagorean theorem that tells us a squared plus b squared is equal to c squared, where a is one side, b is another side, and c is the remaining side. So we know that one side of our triangle is equal to 3. Okay. And the other side of our triangle is equal to 4. Right? And so we would square those to get our remaining side. So 3 times 3, that's what squared means, gives us 9. 4 times 4, which is what squared means, gives us 16, equals c squared. So we have 25 equals to c squared. We need to get rid of our squared. So what we would do is we would do a square root, which negates those. So c would be the square root of 25, which is 5. So that gives us that c is 5, which means that this would be 5 feet, and this would be 5 feet, right? Because they are congruent to each other. Well, now that we know that, all we have to do is go ahead and add all of our perimeter lengths. So, let me take out those boxes so you can see it a little bit easier. Let me just rewrite that. 5 feet. Okay, so our perimeter would have to consist of everything on the outside. So everything on the outside, which means that we would add 5 plus 5 plus 4 plus 4, which gives us a perimeter of 18 feet, right? Because if we add all those together, we get 18 feet. Okay, and that's how we would use all this information about congruency to solve a problem in the real world. Okay, does anyone have any questions or concerns? Questions or concerns, objections? No? Okay. So, what did we learn today? Well, we learned that two figures are congruent if and only if they can be mapped into the other by one or more rigid transformations. So the transformations must be rigid, the angle and the length must be preserved in order for two different shapes to be congruent. Okay? The three types of rigid transformations we have are reflections, translations, and rotations. This means that deletions are not included, which is deletions is what we saw. So a deletion would be a non-rigid transformation, meaning that it would affect the congruency of the figure. Okay? We also saw that if two figures are proven congruent, then the corresponding parts of the figures must also be congruent. Okay? And that applies for triangles and polygons, and that's where we get the congruent parts of a congruent triangle congruence and the congruent parts of a congruent figure congruence. Basically, all just saying, once we know that things are congruent, we can go ahead and fill in those different parts or different lengths to make them congruent. Okay? Any questions or concerns? Okay. Here are our glossary terms that we went over. Our returning definitions we have is reflection, rotation, and translation, which are all types of rigid transformations. And then we got deeper into what it means for two figures to be congruent. Okay? Any questions or concerns? Okay. And And so for tomorrow's an asynchronous day, so you'll be working on Unit 5, Lesson 1, Independent Practice, very similar to how we've done it before. But if you have any questions, please feel free to reach out to me via email.